We'll now consider the transformation of an ideal gas at constant pressure and think about what the constant pressure heat capacity will be. So if we're heating a gas at a constant pressure, we'll typically be heating the gas in a container with a movable piston. So if you see that phrase, movable piston, that's typically indicative of a constant pressure process. As you change the temperature of the gas, the piston can move in or out in order to maintain a constant pressure. Now, to calculate the heat for this process, because the process is occurring at constant pressure, we have to indicate that we've chosen a constant pressure pathway here. So we have to put the subscript P for heat to say that Q is Q subscript P. That's the constant pressure heat. And that's equal to N times Cp times delta T, where Cp is the constant pressure heat capacity. And again, you have to indicate here that we're doing Q sub P because heat is a path-dependent variable, and so you have to indicate that the path that we're choosing here is a constant pressure pathway. So that's why you put that sub P there. Now let's think about what the value of Cp is. In the textbook, they go through a proof that and a derivation that shows where this equation comes from. I'm not going to go through the derivation in this book in this video, but you can see it in the book if you want. And the result of the proof is what we're going to be using, right? That's what we're interested in. So the result of the proof is that the heat capacity at constant pressure is equal to the constant volume heat capacity plus the gas constant R. And this equation always holds true for any monatomic or polyatomic gas. With that in mind, because Cp is equal to Cv plus R for any ideal gas, we can now come up with values of Cv and Cp for monatomic or for polyatomic gases. For an ideal monatomic gas, Cv, we saw in the previous video, was equal to 3/2 R. And for Cp, you're going to have 3/2 R plus another R. So that gives you that Cp is equal to 5/2 R. And I know sometimes that can be a little bit tricky to see for some students. And so I'm just going to add in the step here to say that Cp is equal to Cv plus R. So that's 3/2 R plus R. And in order to add up two values, you have to have common denominators between them. And so that coefficient of 1 in front can be re-expressed as 2/2. And when you do that, what you have here is 3/2 plus 2/2 equals 5/2. So that's where that value comes from. Now, if you have a polyatomic gas, then other forms of motion are possible, right? You have not just translational motion, but you also have vibrational and rotational motion. And so the heat capacities will be larger than what they are for the monatomic gases. So the constant volume heat capacity will be larger than 3/2 R. And the constant pressure heat capacity will be larger than 5/2 R. Let's now consider an example where we're heating nitrogen under two different conditions. So we have 2 moles of nitrogen that are being heated in a rigid container, and we have 2 moles of nitrogen that are heated in a container with a movable piston. I want you to think about which of these two samples of gas can absorb more heat and explain the reason why. That's a really important thing, to come up with the explanation for why, because being able to explain why demonstrates understanding of the concepts that have been discussed over this series of videos here. So think about this. Is the nitrogen in the rigid container capable of absorbing more heat? Is the nitrogen in the container with the movable piston capable of absorbing more heat? Or can both samples absorb the same amount of heat? Take a moment to think about this and put in what you think the answer is. All right, having given you some time to think it over, let's talk about the answer. There are actually a couple different ways that you can come up with the answer to this question. So one way that you can look at it is by recognizing, first of all, that if it's being heated in a rigid container, you're dealing with a constant volume process. And when it's in the container with the movable piston, you're dealing with a constant pressure process. And you can figure out the answer to this simply by looking at the equations that you would have for the constant volume heat and the constant pressure heat. So if it's being heated in the rigid container, then we're dealing with QV, which is NCV delta T. And if it's being heated on the constant pressure pathway, then Q is QP, which is NCP delta T. And what we know is that the value of CV is going to be something greater than 3/2 R, right? Because this is a polyatomic gas. And the value of Cp is some number greater than 5/2 R. Now, remember that heat capacity represents the tolerance for heat absorption that something has, right? And the greater the value of heat capacity, the greater the tolerance for heat absorption. So in the case of our gas that's being heated at a constant pressure, we have a larger heat capacity value and a higher tolerance for heat absorption. And so what we can say is that the nitrogen that's in the cylinder with the movable piston should be capable of absorbing more heat. This can absorb more heat. That's one way you can determine this, just from looking at the equations and analyzing the equations and the numbers. But I think that it's also helpful to get a conceptual basis for why it is that you have a higher heat capacity when you heat the gas at a constant pressure. To do that, I'm just going to wipe the slate here so that I have room to write out another way that you can approach this problem. When you heat the gas in the container that is rigid, when you're heating it at a constant volume, all of the heat gets put into raising the internal energy of the gas. All of the heat goes into raising the temperature of the gas and increasing its kinetic energy. The reason why is because when you heat the gas in a rigid container at a constant volume, no work is being done. But now let's think about what happens when you heat the gas at a constant pressure. So as you heat the gas at a constant pressure, you raise the temperature, and from PV equals nRT, we know that as you increase temperature, and if pressure is constant, the volume must increase. Because the volume is increasing, the gas expands, meaning that the gas does work when it's heated at a constant pressure. This was not possible when the gas was heated at constant volume, right? So that's the key difference between these two cases. When you heat at constant pressure, the gas is doing work. Therefore, you have to put extra heat into the gas because some of that heat is being converted into work, right? Some of that heat is being lost in the form of work. And to make up for that, you have to put in extra heat. And as a result, this gas, heated at a constant pressure, is capable of absorbing more heat. I think it's helpful to have that understanding, having that more thorough understanding of the reason why heating at constant pressure results in more heat absorption, right? So some of the heat is going towards increasing the internal energy, but some of the heat is going into doing PV expansion work. This is why this gas is capable of absorbing more heat overall, right? You have to make up for the fact that when you heat at constant pressure, some of that heat is going into doing expansion work, whereas when you heat it at constant volume, no work is being done, and that's why heating it at a constant volume is not capable of absorbing as much heat. Next up, we'll do some calculations and talk a little bit more about the path dependence and independence of the variables that we've been discussing here.